Hello, everyone. This is another episode of Live Contract Reviews, and today we're going to talk about fungible tokens. And at this call, we're going to discuss two standards. So one is NEP21, which is very similar to Ethereum ERC20 standard, and another one is a proposal for improvement that um, removes some boilerplate that you need to do when you work with the fungible tokens. So let me present a window. Okay, so this is Nomicon.io. This is where Near has some specs and documentation. And here we have a fungible token standard that was published. It has version 2.0, but I think latest is 4.0, so the standard is not really updated. So the standard fungible token interface allows the following. It allows you to create an account internally within this contract. When you do some action, it automatically creates. It has the following methods for calling it. So it has transfer, which is just the alias for transfer from, which takes owner ID as a predecessor. Then we have increase allowance and decrease allowance. And it works similarly how Ethereum ERC20 standard works, where you have an account. Within a contract, you have a balance, which saying how many tokens you have. And then you can set multiple allowances, which we call escrow account ID. So this is the contract which will be able to withdraw from your account some amount. And when you increase allowance, it allows this contract now to withdraw a certain amount more. When they take it out, the allowance automatically decreases. And then you can decrease amount or decrease allowance to bring it back to zero. All these methods are payable in order to pay for the storage, because Near protocol implements state staking. So the idea here is every account that has a contract on it, for example, has to cover the storage of this account and contract state and all the keys with Near tokens. So for example, if the current price is 10 kilobytes or 10,000 bytes for one Near token, and let's say you want to store 300 kilobytes, it means you need to have 30 Near on this account. If you're trying to add more bytes through some transaction, but the account doesn't have it, then it doesn't have a balance to pay for the new state or to cover the new state, then this transaction will fail. It creates a lot of limitations on the contract development right now, especially around contracts that are shared across multiple users. Because the gas is usually cheaper than the storage, so you can create a transaction that increases the storage of the contract, the state of the contract, which requires you to cover with more balance. And if you can do this indefinitely, then you can spam this contract with such transaction until it exceeds the storage. With allowance, you can essentially on one balance on one account just create a very large amount of data on one account, which will blow up the state of the fungible token. and eventually it will stop working and some logic gonna break. That's why we introduced the payable, which requires you to attach some balance that will cover the state increase when you modify the storage. So let's say you modify the storage, the state of the fungible token by increasing the state by 400 bytes, then from your attached balance, you will have to pay this amount to the contract. Yes.
That was a great explanation. One question that I have had for a while about this is 1 kilobyte 1,000 bytes or 1,024?
Yes, it's 1,000 bytes. So it's round for humans, not for machines. So let's go to the implementation of the NFT 21 to basically go through this standard and see how it's done in the code. So we have a structure for account, which has the following. So this is slightly upgraded contract. Let's see. I think it's version 0.4, and it uses lookup maps instead of unordered maps, so the pricing per change is slightly lower. We have a substructure called account. It has balance, it has lookup map, which is an optimized version of an ordered map. We don't need to iterate through them. And then we have number of allowances to track whether we can delete this account or not. When you create, we take a full hash of 32 bytes, and we create the lookup map from this hash. So the prefix becomes unique because nothing that here is 32 bytes. Then within the lookup, actually it's even more because VEC is serialized with 4 extra bytes. We have the following logic. When you, let's say, issue increase allowance, then internal structure checks if there's if allowance is positive, then we insert a new allowance, and if it was not there before, then we increase the number of allowances. If it was there before, we decrease the number of allowances. This allows us to track number of unique escrow or unique allowances per account. This will be important later.
Question on the prefix. Why? It seems like a very long prefix. Don't we usually like to keep those prefixes small to save storage?
Right. Good question. So we need this long prefix because this map is unique per account. So this map will be different. So it's a map within a map. So this is not the main structure, but it's a fun substructure of this map. So we have lookup map for fungible token contract main structure. So let's say you have a hash of chad.near, and this will be a prefix for the your allowances map. And then let's say I have my own map and I will have a different prefix, so our maps do not intersect with each other.
I'm really glad we got to this, by the way, because this is a really good and very important thing. I've seen partners who have kind of done this the wrong way and run into errors that are really hard to track down. So just in terms of like having collections within collections, this is a good model to follow.
Cool. Yes, so, and this type of allowances made this standard a little more complicated, just because now, like because every user or every account state is now not a constant size. So when you add a new account to this, to a token, like let's say I transfer to you, to say that the size of this is constant. So I know if your account didn't exist and I added you, now it's constant. It's some amount of bytes, let's say 400 bytes. But now you can increase this type of allowances multiple times, and the size became non-constant per your account, so it can grow. So the second standard we'll discuss avoids this by having a constant state for every account, constant size of the state. Anyway, so the main structure, fungible token, has two fields. One is a lookup map for account. It takes a hash of the account as a key. A prefix is A, so it's a short prefix. And then the value is the account structure that we just saw. Now, interesting, in order to have any conflicts there, now the size of the keys has to be different as well. So let's say the prefix is A, a small a, and then we use a key, which is just 32 bytes plus 4 bytes for the length of the key. So long as prefix plus size of the key and another prefix do not intersect, or lengths of the keys are different, we'll be fine without any key conflicts. So this is a little more complicated than it should be, but it's not yet improved. Again, this is fairly standard initialization. We take owner ID and the total supply. So owner ID is the initial account that will receive full total supply within a fungible token. And total supply is the number of tokens we mint. There is no precision in this standard because precision is a metadata, not really required to be part of the standard. It's just a good to have. So we check that the state doesn't exist. Then we initialize self. So we initialize the map and the total supply, but we don't return it yet. We get a new account for the owner. We give entire balance to this owner and we save this account to the state, and only after this we return the object. Let's look at the. So there's two methods, increase allowance and decrease allowance. They're very similar. Let's look at the increase allowance. It's called by predecessor, so it's called by you. You already should have some amount of tokens, but not necessary. Increase allowance works the following way. We check that the account is valid. We get the predecessor. We say you cannot add allowance to yourself. We get your account. We get current allowance for the given escrow account, for the given contract. We increase this using saturating add. Saturating add is a Rust helper that allows you to increase integer until it reaches the maximum limit without overflowing. So for example, for 32 bytes integer, it will be something like 4 billion, or 2 in 32 minus 1. And this way, the allowance can be a maximum number without overflowing. And we set it back using this, then we save the account. And finally, we do refund storage. So the way it works is the method is payable. We originally look at initial storage. We call a host method saying, what's my current storage usage? It returns you the number of bytes your account occupies. Then once we did all the changes to the state, we call refund storage, and we take the original amount. We look at the current storage after all the changes in number of bytes. We get the how many near tokens you attached. Then we do a refund amount and doing it the following way. If storage increased, it means you're required to deposit this amount. So we have a storage price per byte in near multiplied by the number of bytes. And we say, if you attached less, let's revert everything you didn't attach enough tokens. And it will revert all the changes you did during the call. Otherwise, we calculate how much you over attached. So let's say you attached 1,000, but you only need 400 of bytes amount. And then if you attached more, we will refund it to you, to the predecessor, using a transfer. And here, if you decrease the storage amount, so let's say you deleted an account or transferred out all tokens, then your account can be deleted. We refund all tokens that you attached plus the amount of storage you released.
Is there a issue to make storage price per byte something that you can get from env, since it could be adjusted in the future?
Yeah, we don't have this issue, but it makes sense to expose, as well as expose all the fees. So maybe I'll provide the values from the config in some free-flow format. So this is how storage refund works. And finally, the way we do accounts is you hash the account ID of the owner, and you say, give me this or a new account with a given hash. And set account works somewhat similarly. When you set a new account, we basically check if the account is non-default, then we need to insert it back into the map. If account was default, which means balance is 0 and allowances are 0, we can basically delete it from the state because you don't really need it anymore. So it kind of handles it implicitly, which is a little strange on how you actually would write something like exchange standard. Let's say I want to move tokens from one account to another. Now I need to think how many tokens I need to attach, if the receiver exists or not. If it doesn't exist, then I need to attach tokens. If the receiver existed, then maybe I don't need to attach tokens. But what happens if there was like my transaction was front run and the receiver was created? So it's a lot of mess to write automated contract that uses fungible token, unless you can ask, hey user, give me enough near to cover for the storage for every transaction. I don't care. I'll just charge you extra. Maybe I'll do refund. Maybe I'm not going to do refunds. So the first standard that we currently use is a little challenging to implement an exchange. And the way exchange would work is you would basically increase the allowance on the exchange by calling a token standard first. And then you will call exchange through another transaction, so exchange can call transfer from your account on your behalf. Similar how ERC20 works, you have transfer from, you say, who the owner, who's new owner, what's the amount. It works the way it checks balances, and then it checks who's calling this. If I'm not the owner, that means I need to have an allowance. If allowance is not enough to transfer, then it's a failure. If not, then we decrease the allowance, then we save the account, create a new account, and finally do a refund of storage. So this is how current old standard works, and we also have a new standard that slightly improves on top of this. So if there is no question on top of old standard, we can jump to the proposal on the.
I think I have two questions. Is the reason why we hash the account ID to sort of obfuscate it from how it's stored in state, or is there another reason?
So one reason is we can standardize the size because hash is fixed size, while account ID is variable size. Second, it slightly prevents you from creating a deep try where you can create something like A, B, A, B, A, B, and so on, which will make it a little more expensive to access the final account. So you can potentially make certain transaction more expensive. But also, so there's two reasons.
Okay. That's great. And then my final question is, I think you might have been explaining this, but I was thinking about something else. But in terms of decreasing allowance, I say that that's payable, but will that ever cost more to decrease allowance?
Good question. I think, yeah, it may not be. So it probably doesn't need to be payable, but because you can only decrease the size of the account state. So, but you still need to do a refund in case you actually set it to 0. Cool. Anything else? All right. So let me present back a window with the standard. So the challenge with this was that it was pretty much just copied from Ethereum ERC20, which has its own set of challenges, such as biggest one, you need 2 transactions to make use of a contract. So let's say you go to Uniswap and you want to swap your token. With Uniswap, you first need to set an allowance towards the Uniswap contract, and then you need to call the Uniswap to do the actual swap. So the second standard, which called allowance-free safe-based token standard, long name to explain the difference. It addresses this issue by combining it into a single transaction. The second challenge comes from Near and our state staking. The state staking is a problem because, as I explained, when you try to implement the Uniswap, you need to know about the state of the accounts, and you cannot make expectation how much deposits you need to do for transfers. So this addresses 2 of them, and the third one is some kind of weird allowance abuse where most contracts will ask you to give unlimited allowance first, and when you do this, that means they can spend all your tokens, not just the amount you want for the given swap. The way this
Wait, say that again.
Works. So let's say you go to Uniswap on Ethereum, and first thing you approve the Uniswap by giving allowance. So if you don't know how much you want to swap, they will usually ask, like, give me all the unlimited allowance, like maximum.
I didn't realize they did that.
I think a lot of the contracts do this because they don't want to like bug you twice.
Got it.
And
Okay.
it'll cost like 60, 70 cents each time or something too.
Just for those approvals. Right. Okay. Yeah. This is something that I'm dealing with the Rainbow Bridge as well, and it's only allowing 10 tokens if you're transferring 10 tokens to Ethereum, and then transferring those. It doesn't just like say,
right.
"Oh,
so
give me access to all of your DAI forever." That seems really bad.
So when you know the exact size, this is cool. For Uniswap, well, you need to approve slightly more for slippage. Right. So rationale for this, we remove extra space that required to store allowance because there's no allowances anymore. Instead of like permanent allowance, we switch it to temporary allowance. When you issue a transaction, it essentially gives the allowance to the receiver instead of having to give it forever. So it removes the extra transaction required to set allowance because it's done in one transaction. It slightly simplifies the usage of the contract because it's a single call. It allows to be chain transaction, which is very relevant to us. So it enables some type of composability through the standard. And we somewhat remove payable. Not really. It's going to be slightly different how we handle it. So it's not really true, but it helps. The way it works is you have two types of transfers. The first transfer called transfer unsafe. It's basically just a regular transfer. You grab the receiver ID and the amount, and we just take your tokens and put it on the receiver's account. That's it. So that's why it's unsafe, because you cannot transfer to a contract. It will just grab it from you. So it doesn't have any logic on the receiver. Second is transfer with safe, and this is the way that most contract transfers gonna handle this. It takes 3 arguments. Receiver is the contract on which you calling. So in this case, let's look at the accounts. Alice is the owner of the token. Then let's call it DAI as a fungible token contract, and Uniswap is an Uniswap contract that will handle a swap of DAI to NEAR. The way you do this, receiver going to be Uniswap, signer and predecessors are Alice, and current account ID is DAI. So this is token standard on DAI. You have amount. This is the maximum amount of tokens that can be withdrawn from your account. Not exact amount, but the maximum. And we will lock all these tokens out of your balance for the duration of the transaction. And finally, payload. This is a string that can be anything that is a JSON string. So you can encode some base64 data into this payload. And it returns a promise. So it doesn't return you a value immediately. Instead, internally what it does, it withdraws the amount from your balance and put it into a temporary structure that we call a safe. So that's stored locally in this contract for the duration of the transaction. The safe contains the following. It has sender ID, it doesn't have it. It has the amount and a receiver. So the amount of tokens that remaining in the safe. So this is what we take. So example can be, I want to swap 500 DAI to NEAR. I, let's say, call this transaction and say amount 500, so safe will be created where amount is 500 and the receiver is Uniswap. So then we store the safe into the storage, persistent storage of the DAI contract. Then we call receiver ID, so the remote contract, with the method on token receive, which gives the following. It gives the sender ID. This is the predecessor. In this case, it's Alice. It gives the amount 500 and gives the safe ID, just some unique number, U64, from which Uniswap can withdraw it. So we call Uniswap on token receive and payload. Payload can be something explaining what type of swap you want to do. So frontend can create this payload and then pass it to this method. What happens on Uniswap is they get called on token receive. Now they know who called them because they have predecessors, so they can verify that DAI called them. They know who sent, how much, and why. This is payload. Payload is why they send it and like what exactly this action is. So payload can explain, I want to swap 500 near towards, or 500 DAI towards like 5 near. And now Uniswap, it essentially blocks this transaction until completion. Oh, and finally what this method does, it attaches a callback on itself called resolve safe. It gives safe ID and sender ID. So the way this works, you call transfers with safe, it calls on token receive on Uniswap, and once this completes, it will call resolve safe back on itself. So now Uniswap within its call can call withdraw from safe back on DAI to transfer the amount from the temporary safe to a different receiver. So it can transfer to itself, or let's say to Bob or someone else, and they can specify amount, how much they want to transfer from the given safe. So let's say because of slippage, they only need to transfer 480 tokens. Then they can just call withdraw from safe, give the safe ID that was passed to them, receiver ID going to be Uniswap, and amount going to be 480. When this is called internally, we will do the deposit to the receiver account. But the internal safe amount will get decreased from 500 to 20 because only 20 remains in the safe. And it can verify that the safe ID is owned by the predecessor, so only predecessor can act on the safe. If there's two calls in parallel, because of async, the safes are not mixed. So let's say Alice called Uniswap twice while this transaction is still flying. The two safes are not going to mix, so they are not going to withdraw from the same balance twice. The balances of Alice is not going to mix because we will withdraw from Alice twice in two different safes. So it saves, so it guards against the reentrancy essentially, and like prevents different balance issues. So Uniswap, when they call this, they should not end their promise. So they should not call it in parallel. Instead, they should depend on the result of this. This is important, so the resolve safe is not called yet. When Uniswap finishes the operation on the safe, like withdraw and complete it, they just ends their call. And this resolve safe is being called on the DAI. DAI grabs the safe ID, see that only 20 tokens left. It puts it back to the sender and returns the amount left, saying like, okay, only like, for example, or like it can return how much left. I don't remember. The standard is maybe a little not updated. And finally, receiving side is explained here. So this is the proposal, and let me know if you have questions on the proposal, or we can jump to implementation of this proposal to explain a little more logic behind the promises. Maybe it will be more clear with some examples. Okay.
Yeah, I think I get this. I think this would be a really fun diagram to have in just a simple Alice Bob walkthrough. I guess I still don't exactly understand like so Uniswap calls the withdraw, and then
Yeah.
automatically the promise will call the what is it called? The final callback.
Yeah, resolve safe.
That's the one. Yeah.
So the reason for this as well is, let's say a Uniswap does not implement a proper API, then it's basically just going to return you tokens, so they're not going to be locked on Uniswap. Because the promise is going to fail immediately, or it can panic at any point. For example, you didn't touch enough gas or some other stuff. In this case, the safe will immediately be reverted back to the original amount. There is slightly more complicated stuff around gas than stuff, because it's a bit more explicit here. So we say for basic compute, we need 5 teragas. For creating a promise, we need 5 teragas. For data dependency, we need 10 teragas. So the minimum amount that I need to pass to a receiver is gas for a promise plus base compute, because it can just do withdraw from safe and return it. The amount of gas for the resolve safe is just a base compute, and it just computes how much gas I need, because it passes all the remaining gas to Uniswap. So also the implementation is slightly more interesting than regular NAP. It does more optimizations. First, it introduces short account hash. It's similar how Ethereum cuts your public key from 32 bytes to 20 bytes, assuming there is enough entropy so they don't collide. Similar, we can do the same here. It's a fixed size, so we say 4 bytes on this. At the same time, we except this one gets the first 20 bytes of hash instead of the last. Account ID, now similarly to NEP 21, it's just a simple balance. It's just 16 bytes, fixed size, pretty good. Safe, this is the structure that was described in the proposal. It only have hash of the receiver ID and the balance remaining in the safe to optimize on the size of the safe. And finally, the standard, well, the main structure has a map of accounts from short account hash, which is 20 bytes, to the account, which is 16 bytes. And this map is essentially every entry is only 77 bytes, which is very small amount of near. If you burn something like 300 teragas of gas, it's enough to pay for the storage through 30% refund on account. But we don't burn it here, so there are still explicit account payments. Second, the temporary structure for safes. Safes only live while the transactions are active. So we do not separately pay for the safes. Next safe ID is just a U64 and total supply is a structure to tell how much total supply is. This is the API, high-level API for calling a receiver, in this case a Uniswap, for example. In the example, this is a callback on our self and implementation. It's somewhat similar. It uses some magic using Rust. So we don't explicitly call hash on the ownership. So as ref converts valid account ID to reference to account ID, and then we have a from implementation on Rust that converts it to a structure short hash account hash, which hashes the account and creates this. So this stuff essentially casts account ID into a short hash by hashing it and truncating it this into. And then we give full total supply to the.
How does the asref get there? I missed that.
Asref is from valid account ID. It returns you account ID by reference.
I see. Thank you.
And then from reference account ID, you can cast it to short account hash. Anyway, so we initialize the structure and give full token. Transfer Unsafe implementation uses two helper methods: withdraw from sender and deposit to account. And it withdraw from sender, it uses predecessor account ID, but it needs a receiver for safety checks. So it's saying you cannot transfer to yourself. You cannot transfer to this token standard, another safety check. And then it basically takes the balance out. And deposit to account is deposits to account that you pass. So in this case, a receiver. And the more interesting is transfer with safe. The way it works is we basically first calculate how much gas we need to pass to a receiver. And if it's not enough, then we panic immediately, so you don't try to do any logic. We take the amount from the sender, again, using this magic helper. So sender is Alice, so we take the amount from Alice. We create a new safe by using next safe ID, increase the increment of the safe. We put that amount into the safe and save the safe into the internal structure. Now we create a promise to, in this case, in the example was Uniswap, and then a callback back to DAI on the promise to Uniswap. We give all the remaining gas, or like some large piece of remaining gas, to Uniswap so they can complete operation and maybe do a bunch of chain operations. So you can attach, if you attach 3,000 or 300 teragas, majority of this gas will land on Uniswap, so they can do some more complicated calls if they needed to. We pass this data. Payload is just a string, so we just pass through this. And then we do a callback on ourselves. And so
in terms of the passing on extra gas to Uniswap, that would be on them when they are calling this contract on your behalf to pass in enough. Like the minimum gas that you can pass is actually wouldn't be enough for something like that, right?
yeah. So Uniswap can basically panic. For example, let's say you need a lot of gas on your side. You can just panic immediately, and it will be okay. So
I
safe
see.
will
So gas to
back.
receiver there is that's an argument that was passed in.
So this is another host function that's saying how much gas was attached to this particular function call.
Mm-hmm.
And then we say how much we need.
I see. So you would do the same thing on the Uniswap side with like, oh, I didn't get enough yet. So this safe would be created, but the promise call to Uniswap would fail because not enough gas is passed on.
So let's quickly go through this contract. I don't think there's a lot of stuff remaining here, and then maybe go to Uniswap to explain this particular receiving part. So withdraw from safe is that called from Uniswap to us. We basically grab the safe out of the structure, saying like, okay, safe doesn't exist. Well, that's a problem. We verify the predecessor matches the hash. If the safe withdrawal is called not by the safe owner, then you cannot do this. So you cannot take someone else's safe. Then we just take this money out of this amount out of the safe and put the safe back, and we deposit to the account. Again, I haven't talked about storage staking yet, and I'll explain how it works here. Finally, when the callback is getting called on resolve safe, we take the safe out. Again, safe should exist because it's from us. And if safe positive, balance is still positive, it means we need to put this balance back to the account. If account doesn't exist for some reason, like you deleted it while the safe was in flight, then we just say these tokens were burnt. So there's not much we could have done. So safe was lost on the way. If account did exist, then we return this money back to the account. Finally, the way we handle storage staking in this account, we introduce two calls called register account and unregister account. Register account works somewhat similarly to refunding originally. You call it, you pay 77 bytes enough of near, and we create this account for you. So if account already exists, it's already exists, nothing to worry about. If account didn't exist, then we basically put the new account in, calculate the difference, refund the remaining difference. An unregistered account right now expects your account to be empty, but I think we should leave this limitation. So if the account balance is positive, it fails. If not, then it doesn't. Then it deletes this account here and refunds you the difference. So instead of being on every call of transfer, increase allowance, decrease allowance, this is handled through these two methods separately. A frontend can handle it. So first time you want to use a Uniswap or a token, it will register your account and you will pay bytes. 1 second.
This is really, really interesting. I've got a couple of questions if we have time or people want to go over a little bit. Wait for a bit. This is super interesting. Have you guys ever heard of this before?
I've heard of it. I haven't dug in. This is great. I don't know why we still have NEP 21. It seems like we should just use this everywhere. It seems superior in like every way.
Yeah, so okay, I'm back. So basically, yeah, so this can be a standard on its own, because this is a common pattern that will be used, for example, on Uniswap as well. Because on Uniswap, in order to provide the liquidity to a pool, well, you need to register your account on Uniswap and pay for the staking on this type. So something like registering an account and unregistering an account, and potentially like have a forced argument which saying burn all my tokens, I don't care, but give me back my storage, is a good standard. And finally, it has account exist method that just verifies if account exists or not. So we almost out of time. I don't know if you guys have a few more minutes, but I want to go to Uniswap to demonstrate how on-receive with safe works. We are not going to discuss entire Uniswap first, just this particular callback. So Uniswap knows which, this is a single pool which works one fungible token and native near token. It verifies that it was called by the fungible token that it's working with. If not, then it's saying no. Then it gets this payload from, as you saw, payload was a string. We use base64 vec-u8, which is expect the string to be in base64 format, and it will cost nearby engine will convert it back to a vector u8, and we just parse it using a Borscht on serialize. So this Uniswap can work with two different calls, deposit and swap for near. So same input on receiving tokens can have two different logical paths based on the payload. But other implementation can do this differently. So it's not limited by the standard. It gets the amount, and based on the payload, it does two different actions. Deposit is somewhat similar. It basically makes sure that the account exists, and it calls, hey, okay, withdraw from safe, and deposit. And once you withdraw from safe, call me back. So Uniswap has a callback on top of this. As you can see, it doesn't check any gas or like similar, like, oh, do I have enough gas to complete all of this? Because if any of this fails with not enough gas, entire thing gonna fail and panic, and it will go back to the token standard and return all the tokens. It knows how much gas it has to attach for withdraw from safe, because the standard said it's 5 teragas is enough. And finally, it basically what it does, it takes the safe, deposits it to itself, but once it's finished, credits this amount to the owner of this. So once that succeeded, this failed, it shouldn't, but it's possible for some reason. It just credits the account of the owner. And on swap, it's slightly more interesting because it knows extra data through the payloads. It knows how much near you want for the US swap. And then it you don't need to have an account on Uniswap to do the swap. So you don't need to do two separate transactions. Basically, you only need to have tokens. Then you can go to Uniswap, issue one transaction to swap your tokens to near. It will call, you will call as Alice, you will call DAI will call Uniswap, Uniswap will withdraw from your balance and give you near. So it knows how many tokens you need to grab from the pool, or like how many near for the desired amount you can get. And instead of taking all of your tokens that you attached, it will only take the required token amount. And at the end, it calls, okay, let's withdraw from the safe. So it doesn't even check the success of this. It believes that the standard that implements a token standard cannot fail at any point. So it just trusts that once I get the money, the required amount, because it verified this through input, go send desired near amount back to the swapper. And essentially that just allows you to do through a single transaction a swap without approval. So obviously Uniswap not gonna authorize your access key to the token standard. Instead, it will just call a wallet to sign this transaction. So this is how the receiving side works. And now when Uniswap wants to do reverse, so this is, for example, swap for tokens. So you pay near and you want to receive tokens. It verifies all your balance, calculates, and then it creates a promise to say, okay, I want to grab your tokens. It's saying, I want to transfer from my Uniswap balance because it knows the balance on the to your account. And then it does a refund for a reason if you don't have an account, but maybe it's a bad idea because it creates an option. So that's how that standard works. I think we should. Yeah.
Are there a couple minutes that you guys are willing to? Yeah, clap, clap, clap for sure. Are you guys down to spend a couple minutes with Q&A, or is everyone antsy?
No, I'm ready to.
One of my first thoughts was, as Chad's question was about like why have NEP21, and I think that like from kind of like a business point of view and all that, people have been using ERC20 for so long that it makes a lot, and it's been so battle tested that it did and probably still does make sense to kind of copy that for a little bit while we introduce these like better ideas, you know, because it's just so simple. I feel like this will take some like proving to the community, like how awesome it is. One like really like high level thought that I had is like, like it was slightly confusing when I was first reading about safes, because it's actually like the word vault kind of makes more sense, because we have like unsafe, and so then you think like security, safety, but then it's actually like a safe, like a bank vault. So just like wording wise, it's like a just small like idea there. Secondly, like I remember when I was reading Mastering Ethereum, the book, I was like, I read this like 5 times. Like I was so confused when they like cut the length of the public key down for the address, and I was like, why would you lose the entropy? So like I understand it's really like entropic, but like I never really understood that, and I don't really know if we want to like emulate that, but that's just like my opinion.
I think from safety perspective, 20 bytes seems it should be enough. At the same time, if you know this problem of like within one, like how many students you need that they have a more than 50% chance of having birthday in the same day. And it seems like a square of, or square root of the number of days in a year. And so square root of this is 10 bytes. It means you need to generate about 10 bytes of SHA-256 keys in order to find the collision. But this is still pretty large number. It means it's like 20, 10 and 20, about the same size. So, or if I'm not mistaken, because it's like 256 in power of 10, which is still kind of looks like a number that cannot be achieved because you need to store all of them in memory in order to find the collision. So a rainbow table cannot solve it for you. So it seems like it's safe. We can go for like 24 bytes if we see like an extra need. At the same time, by the moment the tech capabilities arrive there, we probably can upgrade it.
I guess I'm curious, like if this is all the entropy that's needed, then why are public keys? Why was the length chosen for public keys that was chosen, right? Like I would assume that public keys were given this length because the chances of them colliding is so infinitesimal that it was deemed safe. So cutting them down to 20 bytes or whatever, like remove some of that guarantee. So that's why it feels a little bit weird to me as well.
Power of 2. So 16 is not enough because 16 is probably very realistic to achieve in like 5-10 years. But yeah, for public keys, the next power of 2 was 32 bytes. Kinda.
The future is near.
I actually don't know. I don't know why it was picked. Probably like some logic around math that it makes it easier to compute for some reason.
Going back to the like NEP 21 versus just having everyone use this, to me it seems like if NEP 21 comes into common use, which at this point like the people building on Near are using it, then it kind of hamstrings the effort to have people use this instead, doesn't it? Like I think this, if we want to push this as a standard, it behooves us to push it right from the beginning so that a lot more projects, like the number of projects using it increases the utility by, like that's where it becomes really powerful versus like if there's a mix of this and NEP 21, that's more painful for everyone.
I feel NEP 21 will not be able to do some operations on like Uniswap without first deposit into Uniswap. So it means 3 transactions for a swap. So you first will probably grab allowance, then transfer to Uniswap, and then you will be able to swap. So that seems like on Near it doesn't matter. It's like, well, on Uniswap you can have this a lot, like a key, so you can get it. One more thing I was thinking about on this standard, which is slightly weird, and that I'm thinking whether it makes sense to require a deposit on every single of these two. And the deposit is 1 octannier. So I want to make it prevent people from calling this function without confirming it through wallet. So access keys on Near works only if there's 0 deposit. If this method requires you to deposit at least 1 octannier, it means you cannot call this method through a function called access key. So if I get my access key, log into the DAI contract, then I will not be able to transfer it without going through wallet. it's a little like ridiculous stuff, but it makes some interesting idea because it essentially prevents you from being able to transfer without explicit action. At the same
I
time,
think that's a good idea.
Some methods probably can wrap it up internally. They can introduce like actual transfer wrapper on top, but the standards, like just a token itself, maybe it doesn't.
This also leads me to something that's totally off topic, but like for a future video, perhaps, like how can one prove that they're using a standard? Like I know when you use like Etherscan, you can sometimes even see the code. That would be quite interesting because we are assuming that people are actually compiling this. But I know it can be done, but I don't really know how to prove that the contract that was deployed is the contract they say was deployed.
So we can prove the exact code, but we cannot prove the standard. So let's say you have some slightly custom implementation. If you provide this code, then we can essentially recompile and build it using a Docker build that produces a reproducible binary. So it's the same binary no matter who compiles the code. And this way you can...
Then you compare that to the key on the account?
To the hash, to the hash of the code. So you hash this binary, and if the hash of the code matches the hash that you receive, then you can link it to the source code. Currently, we thought about like putting a JSON file into the core repo. So doing this currently through a manual way, where we just link all core contracts to their GitHub hash on which they will deploy it. And this way we can, in short term, show this data into Explorer. But longer term, it seems like there should be some repo that can do reproducible builds. Automatically, you submit some standard GitHub repo and it produces it and links it, and people somewhat trust it. So that's the way. All right, I think we way over time this time, but this was pretty good session. I hope you listeners learned a lot more on fungible tokens, including promises and the way we think about how they can be composed in near async environment. And I hope the new standard get more adoption. Thanks. Bye.